Hi, my name is Axel. I'm a PhD candidate from Technische Universität Dresden, and this joint work with SAP is about very selective queries and how to deal with them. In our recent work, which has been published on CITO conference, we show tight connection between precise selectivity estimates and good join orderings. And we also showed that sampling generally achieves such precise estimates. However, as it turns out, sampling struggles with highly selective queries, especially if no index is available for some of the highly selective sub-expressions. This work therefore focuses on exactly these situations, where we have to deal with highly selective queries over medium-sized or large tables. We propose a new estimator for highly selective queries that boosts estimation accuracy in these situations and enables a more sound predicate ordering that, especially on in-memory columnar stores, leads to faster query response times. Before we start, I would like to overview some of the cardinality estimation techniques we have at hand and challenges they face. First off, we can use the well-known histograms, which are very good in modeling single predicate selectivities over numerical data. However, they do struggle with modeling arbitrary complex correlation between the predicates due to the curse of dimensionality. And there's also no way that they can capture arbitrary complex expression over string data, like more advanced regular expressions over string data. On the other hand, we see that recent research applies machine learning approaches to the problem of cardinality estimation, and of course, they can handle single predicates, and they are very good in modeling complex predicate correlations. However, the same thing here, they cannot yet model arbitrary complex expressions over string data, like these more advanced regular expressions. And then we have sampling, where we can maintain a sample offline, exploit materialized views, or use it in an ad hoc fashion at query time. And the beauty of sampling is that it tackles all the above issues, because we evaluate some fraction of the real data with the real query or with the real filter. So for a sample tuple, it simply doesn't matter whether it is evaluated on a single predicate, a conjunctive predicate, or an arbitrary expression over string data, because either the sample tuple qualifies or it does not qualify. And out of these reasons, we see that industrial strength optimizers still rely on sampling these days. For instance, SAP HANA samples 1000 tuples at query time to estimate filter selectivities. But here's the caveat. There are some limitations to traditional sampling which we have to address. So traditionally, we sample some tuples from a base table and we can evaluate single predicates over these tuples, like the predicate over age, salary, and project in this example. And of course, we can combine all these predicates to a more complex conjunctive expression. But here's the thing, these more complex expressions tend to be very selective. And we can easily end up in a situation where no sample tuple qualifies this expression. These situations we call zero-tuple situation, or zero-TS in short, and they point to a very severe model limitation, because whenever the selectivity of this expression falls below the sample fraction, we are very likely to end up with no qualifying tuple in our sample. In these situations, query optimizers fall back to basic heuristics and simplifying assumptions like the independence assumption, where they simply multiply individual selectivities and therefore completely ignoring predicate correlations, and which can, of course, also introduce severe estimation errors. So, but before we speak about how we can improve things from here on, we first have to clarify whether it is even relevant to study this case. So is it just a corner case which we can virtually completely ignore, or is there some value to it? To answer this question and assess the number or the frequency at which these zero-tuple situations occur, we analyze the public BI benchmark, which is a real-life user-generated workload with no joins but complex filters, mostly over string data. So this is the first thing I would like to address. The real world cares about string data. And if we were to analyze queries over tables with at least 1 million tuples and use two standard-sized samples of size 1000 and 10,000 tuples, we observed that up to 72% of this workload, depending on the query complexity, leads to the zero-tuple situation, so with no qualifying tuple in the sample. And this is pretty interesting because, contrary to the intuition of being a corner case, this seems to be a rule rather than an exception. And as I said, in these situations, query optimizers tend to use some simplifying assumptions like the independence assumption, which are known to introduce severe estimation errors. So instead of simply assuming independence between all predicates, the first thing one can do is to exploit qualifying sub-expressions. So even if we don't have any qualifying tuple for the combined expression over project, age, and salary, there is little justification to assume independence between salary and age, as we could still have qualifying tuples for this sub-expression at least. And also we can exploit the certainty of the estimate, because sampling is a statistical process which naturally entails some form of certainty. So how does it look like? To model the certainty of our estimates, we use the beta distribution, which is a statistical model closely related to the sampling process. And for any interval A and B, it gives the probability that the true selectivity falls within this interval based on our observation from the sample. So let's have an example. So here we have the point estimate or estimated selectivity of 0.5, which comes from a sample of size 10, where 5 out of 10 sample tuples qualify. Then we could say A is 0 and B is exactly this point estimate of 0.5. And we see that 50% of the probability mass falls within this interval. And this lines up with the intuition that we are equally likely to underestimate and overestimate the true selectivity. So now if we double the sample size and still see that 10 out of 20 sample tuples qualify, we have the same point estimate, the same median in this function, but we see that the slope gets much steeper and more probability mass is centered around this point estimate. And this lines up with the fact that the more we observe, the more we are certain that we are close to the true selectivity. And if 50 out of 100 sample tuples qualify, we are very certain that we are actually close to the true selectivity by estimating 0.5. Okay, but how does it help with selectivity estimation then? So first off, I will start with an example that explains our main technique and does not lead to a zero-tuple situation, but which we can use afterwards to translate it to the zero-tuple situation. So in this example, we are given a sample from a table that contains brands and colors of cars. We have a sample of size 10, and first off, we can derive basic statistics, like the overall probability of observing an Audi, the overall probability that the color of a car is blue, which is 20%, and we also see correlation estimates or conditional selectivities. So under the condition that we have the color blue, we have a 50% chance that the car is an Audi. And under the condition that we have a different color than blue, we also have a 50% chance that the car is an Audi. But these conditional selectivities basically split up the sample into two different size samples of size 2 and size 8. And we can model these conditional selectivities as two different beta distributions, where we see that the point estimate or median in both cases is 0.5. However, we see that the slope of the gray function, which is Audi under not blue, is much steeper due to the fact that we have 8 observations compared to 2 observations for Audi under blue. So more probability mass is centered around the median of the gray function. So to combine all these statistics into one formula, we can simply say the overall probability of observing an Audi equals the probability of observing a blue Audi plus the probability of observing an Audi with a different color than blue, which we can further split up in the conditional selectivities. So far so good, but now let's assume we are given an external statistic that says the actual selectivity of Audi is 0.6 rather than the observed 0.5, like from a one-dimensional histogram. And this clearly renders our statistical equation inconsistent and contradicts our observation from the sample. And to achieve a statistically sound estimate, we have to satisfy the statistical equation. And to satisfy this equation, we can first off increase the probabilities of Audi under blue and Audi under not blue to eventually meet the value of 0.6, which is greater than 0.5. But to which degree is the question? And the trick is that we use the entailed certainty of both beta distributions for Audi under blue and Audi under not blue, which mediate the relative adjustment. So here's what we do. We take the additional probability mass, which comes from the fact that 0.6 is greater than 0.5, and equally distribute it amongst both beta distributions. And as you can see, is that the gray beta distribution absorbs its additional probability mass much faster because we have more observations and more probability mass is centered around the initial point estimate. And this translates to the intuition that the more we are certain about an estimate, so the more observations we have, the less adjustment it should receive. And here we achieve a new estimate for both conditional selectivities, which satisfy the equation and also respect the certainty entailed by both observations. So the main takeaway here is that we can model the certainty of point estimates, and we can use some statistical trickery to consistently adjust the correlations estimates according to their certainty. Okay, so but how does it translate to the zero-tuple situation then? So let's have another example of a sample where we have 10 sample tuples. And here we could ask, what is the overall probability of observing a red Honda? As you can see, there is no red Honda contained in our sample. However, we first start with deriving these basic statistics again, like the overall probability of seeing a Honda, or probability of observing the color red, and also the conditional probability of seeing a Honda under the condition that is not red. As we see, 4 cars are not red, out of which 3 are Hondas. We have a point estimate of 0.75 for this conditional selectivity, which we can again model as a better distribution, where now the median or point estimate is 0.75. Again, 50% of the probability mass on the left side, 50% of the probability mass on the right side. But now is the question, what is the probability of Honda under red? So from the sample, we will simply derive that it is 0, right? However, we also note that the sample is very limited in its size and what it can actually model, especially if we constrain it to the color red. And instead of just saying it is 0, we use an unbiased estimate, which you can find in the paper. And this unbiased estimate depends on the sample size and enables us to model yet another better distribution. And as this unbiased estimate is clearly not 0, it introduces an inconsistency to our statistical equation just like before. But again, just like before, we can adjust the conditional selectivities with respect to the entailed certainty to satisfy this equation again. And this eventually leads us to the estimate that 2.4% of all cars are red Hondas based on this observation from the sample. And this is pretty interesting because without any actual observation of red Hondas, we still achieve a statistically sound estimate from the sample without falling back to the independence assumption. So the main takeaway here is that you can use an unbiased estimate of the conditional selectivity Honda under red and adjust this unbiased estimate by exploiting the certainty of Honda under not red, which you can observe from the sample. The next step is to extend this idea to an arbitrary number of predicates, not only 2, which you can find in the paper, and I will not detail it here, but the basic idea is to recombine sub-expressions that still lead to qualifying tuples and to estimate correlations between sub-expressions that cannot be directly observed from the sample. As for our evaluation, our paper shows a very extensive evaluation where we use 50,000 queries over several data sets to analyze the effect of distinct values, skew, and correlation. And in this experiment here, we report the multiplicative error or Q error for 10,000 queries with 7 random range predicates in a conjunction. We use different sample sizes and report the maximum and average error. So depending on the sample size, we have a different likelihood in ending up in a zero-tuple situation. So because the greater the sample size, the less we are likely to end up in a situation where no sample tuple qualifies the query. If no sample tuple qualifies, we of course use our technique, which I explained so far. And if we have at least one if we have at least one qualifying tuple, we use the traditional estimate, which is number of qualifying tuples divided by the sample size. We compare our estimator to 2 different groups of estimators, which we tag under lightweight and heavyweight estimators. And the lightweight estimators are some basic heuristics which we have identified as fallback strategies for query optimizers. And the heavyweight estimators are more sophisticated models like machine learning approaches. So first off, let's focus on the lightweight heuristics. So the first thing, without detailing every number here, is that all these heuristics use some form of independence assumption. And if you were to compare these numbers to the numbers of other experiments, you would come to the conclusion that these estimates are basically all over the place. And the performance of these simple heuristics really depends on the dataset you evaluate them on. So there is no single best. As for the more advanced models like artificial neural networks, the combination of histograms and sampling, and the kernel density estimator, we observe the interesting fact that as soon as we start to use moderate sample sizes, in this case, a sample with a sample fraction of 0.4%, we start to outperform these more advanced models. And this leads us to the conclusion that sampling actually is really reliable in non-zero tuple situations already. And as soon as we start to exploit qualifying sub-expressions and to use the certainty between estimates and to estimate correlation between sub-expressions that cannot be directly observed, we become competitive again or even outperform these more advanced models. So the last thing I would like to address is the cost of suboptimal plans due to the zero tuple situation. In this experiment, we use several queries with 2 to 7 predicates in a conjunction, which entail a different degree of correlation, and of course all queries lead to the zero tuple situation. As a standard approach, we simply sort the individual predicates according to their single selectivities. And our model, on the other hand, allows for a more sophisticated predicate ordering, which respects the predicate correlation. And in this experiment, you can see that the more complex the query becomes, so that means the more predicates are contained in the conjunction, the more important it becomes to take the correlation into account, as you can really reduce query execution time. So in conclusion, I hope that our paper and this presentation could emphasize the fact that sampling is a very universal and good estimator already. However, it struggles with very selective queries. To address this issue, we propose a new estimator that boosts estimation accuracy and enables a more sound predicate ordering in these situations. However, the most outstanding point is that it allows for seamless integration into existing optimizer infrastructures. We implemented our estimator into a prototype of SAP HANA, and we report on the right side the relative speed up, depending on the predicates that are used in the query. So what you can see is that if all predicates in a complex query are independent, we don't achieve any speed up whatsoever, because there is no correlation for us to exploit and the basic heuristics are actually good. But as soon as we start to observe correlation or anti-correlation within the predicates, we achieve a considerable speed up, which is even more pronounced if the plan is cached beforehand. Okay, so that's everything. Thank you for your attention, and now I should be ready to take your questions.